Welcome to the course. I'm CyberEd, and today we're kicking off Chapter 1 of your CCNA journey. We're going to break down how networking started, how the internet evolved, and why understanding these fundamentals is so important in the real world. Let's jump straight in. Starting a journey into networking means learning how computers communicate and how the internet, our largest global network, operates. Networking is one of the most in-demand areas in IT, powering everything from hospitals and schools to government, businesses, and cloud platforms. Because almost everyone relies on the internet today, organizations continually upgrade and expand their networks to support new services, high traffic, and global collaboration tools. The Cisco Certified Network Associate certification prepares you for entry-level networking roles. Despite the associate title, it is widely respected and often required for networking jobs. CCNA builds a strong foundation in designing, configuring, operating, and troubleshooting small to medium-sized enterprise networks. You'll learn network access, IP connectivity, IP services, routing and switching concepts, and essential security practices. Before the internet existed, researchers and institutions were exploring ways to connect computers across long distances. Their earliest major success was ARPANET, a project created in the late 1960s and funded by the US DoD. ARPANET used packet switching, a method that allowed computers to split data into packets and send them across a shared network. Although revolutionary, the early network lacked the resilience needed for large-scale communication. In the early 1980s, the Defense Advanced Research Projects Agency introduced the TCP/IP protocol suite, which ARPANET adopted as its standard. TCP/IP provided reliable communication, standardization, and scalability, allowing ARPANET to grow into larger interconnected networks. This expansion eventually became what we now call the internet. Today, the internet is a global mesh of interconnected LANs and WANs, constantly expanding as more devices come online. No single organization owns the internet, but several bodies maintain standards, coordinate resources, and ensure global stability. Key internet organizations. So you got IETF, develops and promotes internet standards to keep the internet operating smoothly. You got IANA, manages IP addresses, protocol resources, and the DNS root zone. And you got ICANN, oversees global coordination of domain names and IP address allocation to ensure stability and consistency. Now that the history is clear, the next step is understanding how different network sizes are structured and used. A network can be as simple as a few devices connected together to share files, printers, or applications. Instead of physically moving data with USB drives, users across shared resources like a file server or printer directly over the network. Local area network. A LAN is a small network contained within a limited physical area, such as a home, office, or a single building. For example, imagine ACME's headquarters. All devices in that building, computers, printers, servers, and storage, connect to the same LAN. Employees can print documents, share files, and access applications hosted on local servers. Small office, home office, SOHO. If ACME opens a small remote branch in another city, branch A, this new site is considered a SOHO network. A SOHO network is smaller and simpler than the main corporate LAN, but still needs access to central resources like CRM databases or application servers located at HQ. Cloning the HQ servers at branch A would cause data sync problems and delays. A better long-term solution is to link both locations through a larger network. Wide area network. A WAN connects LANs across long distances, cities, countries, or continents. With a WAN, branch A can access HQ servers in real time without needing local copies. Modern WANs are provided and maintained by service providers and internet service providers. They offer technologies that extend a company's LAN over wide geographic areas. Common WAN services, like Metro Ethernet, extends a customer's LAN across a city using the provider's network. Virtual Private LAN Service, VPLS, creates a large virtual LAN that spans multiple locations. And then we have multi-protocol label switching, connects networks across multiple service providers, enabling international WAN connections. WAN services allow organizations like ACME to link all of their branches together, ensuring employees everywhere can access centralized resources efficiently. For devices to communicate over a network, they must follow a common set of rules, known as a protocol suite. A protocol suite defines how data is formatted, how messages are sent and received, how devices identify each other and handle errors. In the early days, vendors created proprietary protocol suites like AppleTalk and IPX, SPX, which often only worked with their own equipment. This didn't scale well. Today, networking is standardized around the OSI reference model, theoretical, used for learning and troubleshooting, the TCP/IP protocol suite, real-world implementation used on the internet. The OSI model is a 7-layer framework created by ISO to describe how data moves through a network. It is not implemented directly in systems, but it's essential for understanding and troubleshooting networks. Layers, we go from top to bottom. So we got the application layer. Interfaces we use as applications like HTTP, FTP, SMTP, DNS, etc. Then we have presentation, formatting, compression, and encryption, decryption of data. Then we have session, creates, maintains, and terminates communication sessions. Then transport, segments data, uses ports, and handles reliable or best effort delivery, TCP/UDP. Network, logical addressing and routing, IPv4 and IPv6. Then we got data link, framing, MAC addressing, and error detection, LLC and MAC. And then we got physical, actual transmission of bits over the medium, copper, fiber, and wireless. A common mnemonic for the 7 layers are, all people seem to need data processing. And that goes from application to physical. Always good to remember. Encapsulation and PDUs. When data is sent, it moves down the OSI layers and gets additional headers, trailers at each layer. This is encapsulation. At the receiving device, it moves up the layers and headers are removed. De-encapsulation. Each layer has a PDU, protocol data unit. Layers from 5 to 7, data. Layer 4, segment. Layer 3, packet. Layer 2, frame. Layer 1, bits. Layer 7, application. Closest to the user. Provides network services to applications like web browsers, email clients, and file transfer tools. Examples of application layer protocols: HTTP and HTTPS for your web browsing, FTP for file transfer, SMTP, POP, and IMAP for emails, DNS, name resolution, DHCP, automatic IP addressing. At this layer, the PDU is data created by the application. Layer 6, presentation, responsible for how data is presented to the network and the receiver. Formatting, converting character sets, data structure formats. Then compression, reduces size for faster transmission. And then we have encryption, decryption, secures data in transit. PDU is still data. Layer 5, session, manages communication sessions between devices, establishes a session, maintains it while data is exchanged, and terminates it when communication is done. PDU remains data. Layer 4, transport. The transport layer moves data between applications on different hosts and introduces the concept of ports. It breaks data into segments and reassembles them, tracks multiple conversations between hosts, and uses port numbers to deliver data to the correct application. Well-known ports 0 to 1023, common services HTTP, HTTPS, DNS, etc. The registered ports 1024 to 49,151, and these are vendor-specific applications. Then you have dynamic ephemeral ports 49,152 to 65,535. These are temporary ports used by clients. Example of well-known ports FTP 2021. Then you have Secure Shell 22, Telnet 23, SMTP 25, DNS 53, HTTP 80, POP3 110, IMAP 143, HTTPS 443. Now we're going to go into TCP versus UDP. At layer 4, two main transport protocols exist. You got Transmission Control Protocol, which is TCP, connection oriented, uses a three-way handshake, SYN, acknowledge, and acknowledge, provides reliable delivery, acknowledgements, retransmissions, and it's used by applications where accuracy is critical, like web, email, file transfer. Then you have User Datagram Protocol, UDP. This is connectionless, best effort delivery, no acknowledgements, no retransmissions, lower overhead and faster, used where speed matters more than reliability. At this layer, the PDU is called a segment. Layer 3, network. The network layer is responsible for logical addressing and routing. Main functions: assign and use IP addresses, IPv4 and IPv6. It encapsulates data into packets with source and destination IP addresses. Routes packets between networks using routers. Key points to take away: protocol, IP, connectionless, best effort, no guarantees. IP is independent of the physical medium, works over copper, fiber, wireless, etc. Routing protocols and routers operate here. PDU at this layer is the packet. You'll study NAT later, where private IPs can be translated into public IPs. Layer 2, data link. The data link layer prepares data for placement onto the physical medium and handles local delivery on a single network segment. It has two sublayers: LLC, which is logical link control. It encapsulates layer 3 packets into frames, adds layer 2 header and trailer. Trailer includes FCS, frame check sequence, with a CRC value for error detection. Media access control, MAC, works with the network interface card, and it uses MAC addresses for local network communication. MAC addresses has a 48-bit, 6 bytes, and is written in hexadecimal. The first 24 bits is the vendor ID, the last 24 bits device specific, often called burned-in address. At this layer, the PDU is a frame. Layer 1, physical. The physical layer deals with the actual transmission of bits across the network medium, and this converts frames into signals. And that's where you have electrical, which you have copper, then light for fiber, radio, wireless. Defines cables, connectors, and signal standards. PDU is a stream of bits, ones and zeros. Network media and Ethernet basics. Almost every wired network today uses Ethernet, defined by IEEE 802.3. Ethernet standards define how signals are transmitted, supported speeds 10 megabits per second up to 10 gigabits per second and beyond, allowed cable types and distances. Then you got copper cabling, UTP, STP. You have two common types, UTP, unshielded twisted pair, cheaper, common in LANs. And then you have STP, shielded twisted pair, has shielding to reduce EMI, is a little more expensive. Common categories, you have Cat3, which runs at 10 megabits per second, and the cable can be up to 100 meters long. Then you got Cat5, 100 megabits per second, up to 100 meters. Cat5e, 1 gigabit per second, up to 100 meters. Cat6, 10 gigabits per second, is between 37 and 55 meters. Cat6a, 7, 10 gigabits per second, up to 100 meters. Copper suffers from attenuation, signal loss over distance. Fiber optic cabling. Fiber uses light pulses, LEDs or lasers, instead of electrical signals. Benefits, you get higher bandwidth, longer distances and less signal loss, immune to EMI, RFI. The drawbacks with this is more expensive and more fragile because it has a glass or like a plastic core. You have two modes, which is single mode fiber, SMF, has a small core, uses lasers, and goes long distances between cities. And then you got multi-mode fiber, MMF, and this has a larger core, uses LEDs, and is shorter distances inside LANs. Understanding the TCP/IP protocol suite. The TCP/IP suite, developed by the US DoD and maintained by the IETF, is the real-world protocol suite used on the internet and modern networks. It's commonly represented as a 5-layer model, which maps to the OSI model. So you have one application combines OSI layers 5 and 7, 2 transport, same as OSI layer 4, which is TCP UDP, then 3 network, same as OSI layer 3 IP, data link similar to OSI layer 2, and 5 for physical, which you have similar to OSI layer 1. TCP/IP is implemented in all network devices, PCs, smartphones, servers, routers, switches, etc. Modern networks rely on many different devices, each with its own purpose. This section covers the core network devices you'll encounter: hubs, switches, routers, firewalls, IPS, IDS, wireless access points, controllers, endpoints, servers, and Cisco's recommended architecture models. Hubs, legacy devices. Hubs are outdated and rarely used today. They forward any incoming signal out of all ports, causing broadcast storms, causing unnecessary network noise, collisions when devices transmit at the same time, poor security since everyone receives everyone else's traffic. Hubs use a contention method called CCNA/CD, where devices listen before transmitting. Modern networks avoid hubs because they create congestion and have no intelligence. Layer 2 switches. Switches replace hubs by forwarding frames only to the intended destination. The key features: it operates at layer 2 data link, forward based on MAC addresses, build a CAM table, MAC address table dynamically, and reduces broadcasts and prevent collisions. MAC learning process. A frame enters a switch port. The switch records the source MAC and associates it with that port. When sending traffic, the switch uses the MAC table to forward frames directly. If the destination MAC is unknown, switches send a broadcast. PCs also keep an ARP cache, IP to MAC bindings. Layer 3 switches. Layer 3 switches combine switching and limited routing. They read IP packet headers, perform inter-VLAN routing, offer better performance than routers at LAN speeds. However, they don't replace routers for advanced WAN or edge functions. Routers. Routers operate at layer 3 and interconnect different IP networks. Core function: it reads the destination IP addresses, consults the routing table, forward packets toward the correct network, act as a default gateway for LANs. Firewalls and next generation firewalls. So firewalls protect networks by filtering inbound and outbound traffic. They sit at the network perimeter. Default behavior: allow traffic going from inside outside. Block unsolicited traffic coming from outside inside. Security zones. Cisco's firewalls use trust levels 0 to 100. Inside 100 trusted, outside 0 untrusted, DMZ 50 semi-trusted, used for public-facing servers. NGFW capabilities: it has deep packet inspection, malware and ransom protection, VPN support, application level filtering, and integrated IPS modules. Intrusion prevention systems: IPS and IDS. IPS inspects traffic in real time, blocks malicious traffic immediately, uses signatures, can be tuned with custom rules. IDS receives copies of traffic, detects attacks but cannot stop them, sends alerts only after detection. Modern Cisco devices integrate IPS into the firewall for single pane management. Access points: APs extend a wired network into a wireless one. Benefits: mobility for users, no need for cabling, supports bring your own device environments. Frequencies is 2.4 GHz, longer range, limited channels, high interference. 5 GHz, shorter range, many channels, less interference. We'll study wireless design later. Cisco Wireless LAN Controller, WLC. When organizations deploy many APs, managing each one individually becomes impractical. A WLC provides centralized control, configures all APs from one interface, push updates and security policies, and manages large WLAN deployments efficiently, used in enterprise networks with many floors or buildings. Endpoints and servers. Endpoints, laptops, desktops, tablets, phones, consume resources. Servers provide resources such as file sharing, web hosting, directory services, etc. A centralized file server stores documents for all employees instead of each device storing them locally. Cisco DNA, Digital Network Architecture. Cisco DNA is a software-driven platform that automates network configuration, provides analytics and monitoring, enhances security, integrates with Cisco's hardware across the enterprise. It's used for modern intent-based networking. Network topology architectures. Designing a network requires planning, understanding requirements, and choosing appropriate equipment. Cisco provides Cisco Validated Designs, CVDs, to guide engineers with proven, scalable architectures. So we have the Cisco two-tier architecture, collapsed core, used for single buildings or smaller campuses. Layers. Layer 1, access layer, connects endpoints, PCs, printers, phones. Layer 2, distribution layer, and this is known as the collapsed core, as redundancy for access switches. Layer 3, routing, ACLs, quality of service, and policies. Switches at the access layer usually have only one connection to users, but distribution switches connect redundantly to each other. Problems with daisy chaining. Daisy chaining creates no redundancy, failure propagation, poor performance. Hence why hierarchical architecture is recommended. Cisco three-tier architecture, used for large campuses or multiple interconnected buildings. You have 3 layers: the core layer, high-speed backbone connecting buildings; layer 2, distribution layer, routing, filtering, and redundancy. You have layer 3, which is access layer, user device connectivity. The benefits of this: better scalability, more redundancy, improved performance, easier management. The core links distribution switches from multiple buildings and connects to edge routers for WAN internet access. That's the end of chapter 1. We'll go through the summary. This section we covered the primary network devices and architectures you'll work with as a CCN engineer, hubs, which are obsolete, switches, MAC-based forwarding, layer 3 switches, routing and switching, routers, connect IP networks, firewalls, traffic filtering and parameter security. Then you have your IPS/IDS, which is threat detection and prevention. You've got your access points, wireless connectivity, WLC, centralized AP management, servers and endpoints provide consume resources, Cisco 2-tier and 3-tier designs, recommended architectures. These fundamentals are essential for understanding real-world networks and preparing for the CCNA exam. I'm CyberEd, I'll see you in chapter 2. Peace.